It's the age-old question. If a tree falls in the woods and no one is there to hear it, does it make a sound? Well, first of all, what exactly is a sound? Sound is a wave, but so are lots of things. More specifically, sound is a wave made of vibrations in the air. When something makes a sound, it vibrates the air molecules, which sends a chain reaction through the air until it reaches our eardrums. When our ears pick up that sound, signals are sent to our brain so that we can interpret what we're hearing. So based on that physics definition, the tree really does make a sound whether someone is there to hear it or not. In space, no one can hear you scream, and as scary as that statement may be, that shouldn't be altogether surprising. If sound waves are vibrations in the air, then take away that air and bye-bye vibrations. Sound waves need a medium or material to travel through. These kinds of vibrational waves have another name, longitudinal waves. In fact, there are two main types of waves, transverse and longitudinal. Longitudinal waves are where the vibration moves parallel to the direction the wave is traveling. A slinky can help us understand this, because a longitudinal wave can be created by pushing a slinky along its length, sending a pulse across it. Transverse waves, on the other hand, is where the vibration is at 90 degrees to the motion of the waves. This time we have to move the slinky side to side. Light waves and water ripples are transverse, but sound waves are longitudinal. Scientists love to name things. It's not enough to name the wave itself, we also need to name some of the wave's features. Two of these are called compressions and rarefactions, as shown here. A compression is a high-density part of the wave, the part where the slinky is compressed. It is the peak of the wave. A rarefaction is a low-density part of the wave, the part where the slinky is most spread out. This is the trough of the wave. One difficult part of understanding this topic is the question of why these compressions and rarefactions are considered to be a wave at all. After all, it doesn't look very wavy. But if we plot particle density across the image, we can see how we know that it is a wave. Much more wavy, don't you think? We can also use this diagram to measure the so-called wavelength of the wave. This is the distance between two identical parts, from a compression, peak, to the next compression, or from a rarefaction, trough, to the next rarefaction. A wavelength is the length of one full wave in meters. Last but not least, frequency. A sound wave's frequency is a number that tells you how many waves pass by each second. Frequency is measured in hertz, Hz. So for example, 60 hertz, the frequency of most TVs, is 60 waves per second. Or in the case of television, this means that the picture refreshes 60 times a second. A high-frequency sound is high-pitch, like a high note on a piano. A low-frequency sound is a low-pitch, like a tuba. So what are some uses of sound? The average humans can hear with a frequency between 20 Hz and 20,000 Hz. But there are also sounds we can't hear. Ultrasound waves are too high frequency for us to hear, but they can be of great use to us. Ultrasound waves are used widely in medicine. Ultrasound machines bounce sound waves off the inside of your body to produce an image. We can use this to detect blood clots, assess stomach injuries, and create images of babies inside their mother's wombs. Bats also use sound waves for navigation. They send out ultrasound pulses, which bounce off the walls and return to their ears. In this way, their brain can create a picture of their surroundings that is as accurate as human eyes. This is called echolocation because the sound waves echo off the walls. Dolphins also use echolocation underwater. Sounds are vibrations in the air that travel to your eardrum and get interpreted by your brain. When we plot air density, we see that sound is a longitudinal wave. This is different to a transverse wave, such as light, because the vibrations are parallel to the direction the wave is moving. Sound, like all longitudinal waves, requires a medium, material, to move through. Sound cannot travel in space, for example. Sound waves contain high-density compressions, peaks, and low-density rarefactions, troughs. They have wavelengths, the distance peak to peak, and frequencies, the number of waves per second. High-frequency sound waves are high-pitch, and low-frequency sound waves are low-pitch. Not only are sound waves useful for human senses, but bats and dolphins use them instead of eyes to create a picture of their surroundings. These high-frequency sound waves are so high-pitched that we humans can't hear them. But we can use them in medicine to create pictures of certain parts of the body, most commonly to take photos of an unborn child.